Well, hello everyone. Thank you for coming this afternoon into the OCP Regional Summit here in Prague. Such a great place to be here in Prague. It's beautiful and I've enjoyed myself thoroughly. But I'm going to get on to some things that I think are really important to all of us. I'm going to talk to you guys a little bit about getting to net zero and lowering your carbon emissions. My name is Sean Varley. I'm the Vice President of Product Marketing at Ampere Computing. And I've been in the industry for 30 years, and I'll echo my colleague Madhu Rangaranjan earlier, who said this is the most fun I've ever had in my professional career, really focusing on something that is not only for the good of the industry, but for the good of the environment. And I'm going to talk to you a little bit about that. If any of you have or were at some of the sessions earlier today, such as JP's session or the panel that Priya ran, you will have heard a lot more about the activities that are going on now to really address sustainability from a data center and a data center perspective in the industry. And really what that is all angled at is really addressing PUE and the substantial amount of efficiency that can come out of delivering power more effectively. But what I'm going to talk to you guys about is slightly different than that. And I'm going to get to what Gerard talked about, which was the 1O, or the 1 in the PUE equation, which is the substantial amount of power consumed by the data center itself. And we want to address that at its heart, at the core, if you will. And so we created a company that actually addresses that. Ampere is a semiconductor company that builds cloud-native processors, and we build that for sustainable computing. This is very, very different than what's been used for the last several decades in the industry. And we'll talk a lot more about what that is, but before we get there, I want to make sure that we're all on the same page. You may have seen this slide earlier, but it bears repeating. Our industry and what happens with data centers in general is that they consume a lot of electricity, right? And they consume quite a bit of water. And so what's happening with that is that you find that, and this is from Climatique, that 2.5 to 3.5% of the global greenhouse gas emissions are now created by our industry in cloud computing itself, which is a substantial amount, as much as some of these others that you see here, such as aviation or rice cultivation. From my home area in Sacramento, California, there's a lot of rice produced there. This is a significant amount of greenhouse gas that is produced by our industry, and we want to get to the center of this by addressing the core of the problem rather than the PUE efficiency problem, which I admit is an excellent way to focus on sustainability. But let's get to the core of the problem. Now, we have recently released a lot of information about data center efficiency from our perspective, which goes into a substantial amount of modeling, and this is all modeling based off of real-world benchmarking of our servers against the legacy x86 ecosystem. And this shows here that you can get 2.5x better performance per rack. Why is that important? Because you're packing a lot more compute into a cubic meter or a rack, whatever measure you want to take to actually measure the compute itself as a resource for services. And not only can you do this in fewer racks, which we're showing here, 1/3 the rack space to actually house the service, but you can also do it with 2.8x less power. And this is, again, addressing the 1O that JP and Gerard and others are talking about when they talk about PUE. So the 1O is what we're actually consuming. Let's reduce the amount of power that we're actually consuming to do that kind of computational work, and that is what services are done. Now, this particular study was done with web services, a very common workload in the data center today. That web service was composed of a number of different applications. Typical tiered service, front end, middle tier, which is doing caching and key value stores with popular applications like Nginx, Redis, Memcached, and then a back end with a database. In this case, we used MySQL, but we could have used many, many others. MongoDB, Cassandra could have been in there. There's a number of different applications that we could have used to model the service. Now, this is substantial savings. We like to say you can do a lot more with less. These are because of design choices that Ampere has made in designing processors. Now, a little bit more information that kind of goes along with this modeling. So we look at a rack. A rack is ubiquitous in our industry. It's so ubiquitous that it becomes a really good tool to measure compute density because you are inherently space constrained in a 42U rack. Some racks are larger than that, but 42U or units is the common measure. And you're also constrained in power. So here I show you a striation or a set of power budgets for racks. Some racks in maybe power constrained environments at the edge or in small central offices or even like campus kinds of data centers might be running at 4 kilowatts, somewhere in that range. And then you can see it ranges up. And it can even range higher than what I've shown here, but this kind of hits the common middle of the road sort of rack budgets that you'll find out there in the industry today, 4 kilowatts to 16 kilowatts. Okay, across that striation of racks and rack power budgets, which you'll find from the edge all the way to the hyperscale CSP, what you'll find with a typical application that I mentioned earlier, in this case Nginx, which is a front end for web services, very ubiquitous in this industry, is about a 3 to 4x advantage in performance per rack. This is a critical measure because this really is a measure of compute performance density, which is really core to lowering the amount of equipment it takes to actually run services in data centers. We can also pack over 4x the number of cores into a rack. So if your workloads are inherently sort of compute limited from a computational standpoint, then the number of cores that you can pack into that sort of cubic meter that I was talking about is really, really important. The legend here is that the dark black is one of the legacy x86 vendors, and then the darker gray is the other one. So let's look at my theory, and I'm going to really kind of get down to a very simplified theory. JP earlier talked about some I think more complicated models around sustainability. Mine is much more simple, but I think it kind of hits the heart of the matter. If you want to get to a path to net zero, let's look at what it takes. And I've got a simple kind of balanced scale here. A couple of weeks ago, I was in Iceland and I saw these scale weights that were dug up from some place in near Reykjavik that were like 800 or 900 years old. And so I kind of got fixated with scale weights, and so forgive me. So here we have operational carbon, which is in JP's discussion earlier. This is the electricity required to run the data center. Scope 2, if you're into scope analysis language, operational carbon is emitted as you consume electricity in the data center. Embodied carbon is what it takes to, is really scope 3, and that is the carbon that's captured in equipment, the things that are actually in data centers. Everything from concrete to racks themselves and metal and machinery and the servers themselves and networking and everything that goes along with it. So that embodied carbon is also important because it does take carbon to produce all of this stuff. Now, on the other side of the scale, we have renewable energy, which is that green scale weight, and also carbon offsets. I am going to completely discount carbon offsets here because I think they're a distraction. And I think a lot of people would agree with me. They are a distraction because what we really want to do, if we want to address these issues that are facing our societies and us as a race, we need to reduce our consumption. And that is going to get really into building many, many more renewables. So I'm going to talk to you a little bit more about how embodied carbon can also be translated a little bit into operational carbon. Remember, this is the actual electricity consumed. So as we go through this talk, I'll show you a little bit more about how you save equipment also becomes an operational savings. Now, to balance the scale and to get to net zero, let's help things out. Everybody is doing a lot to make data centers more efficient from a PUE perspective. But what's not really being addressed is fundamentally lowering the amount of electricity that the actual data center consumes itself. It's almost like as an industry we've shrugged and said, it's going to take this much. Let's just keep working over here for a while. No. This is not what our argument is. Our argument is lower that electricity bill, lower the amount of electricity that it takes to actually get things done. And that is what we have done with cloud native processing. So we're balancing the scale by taking the operational carbon and reducing it. Taking the embodied carbon and reducing it. Those are smaller scale weights. They may not be obvious. Now on the other side, this other side is renewable energy. Now, I really enjoyed JP's discussion earlier today because he talked a lot about things that are on this, the RECs and the PPAs and the things that we're doing to actually enable more renewables. We need this. This is a huge piece of the equation. That bigger renewable energy weight is going to be part of this equation, which is going to balance the scale and get us to net zero. All right, so we took the data that I showed you earlier, where you've got, this ultimate, 2.5x performance factor, the 1/3 the space, 2.8x lower power. This is around our modeled web service. We scaled that up to a data center level. Now, in this case, I used a data center which had a lot of public information around it. It was actually the NSA data center in Bluffdale, Utah, if anybody really wants to look it up. It's a 100,000 square foot data center, 66 megawatts, about 4,000 racks. The space required for each rack, about 16 square feet. And then I used 11 cents, which is the published government number for average cost of electricity in the United States right now. And then I assumed a PUE of 1.2. And so by doing this, I scaled that model up to that 100,000 square foot data center. And the savings just scales sort of linearly, really. There's not a lot of magic to this math. If you can save 50% of the servers that you need to do something useful, the service, in this case a web service in the data center, then you can save 50% of the operational carbon and about 50% of the embodied carbon in that data center. This is a massive change. So if you can triple your data center efficiency, you can affect this at a global scale. By basically, the numbers came out here for operational carbon that in the legacy instance number 1, we had 334 metric tons consumed in that 100,000 square foot data center. In the other legacy x86, it was 217,000, those are thousands of metric tons of carbon. And in the Ampere case, it was 134. So we're talking about over 50% savings against legacy x86 on the operational side alone inside of this modeled web service data center. And on the embodied carbon side, might not be obvious, but these little guys here are rows of racks. So you kind of have a choice. 1 row, 2, 2 or 3 rows compared to the legacy way. This is what I'm really getting at. If we look at the amount of equipment it takes to actually get something useful done, we can actually make huge, huge savings. All right, I told you I would talk to you a little bit more about how to get more operational carbon eliminated by reducing the amount of embodied carbon. So if we look at this model and we go from I'm using my one rack to 3 racks comparison here, there's a lot of other things that go with a rack, right? The rack itself, additional cables for networking, all of the power delivery equipment, the top of rack switches themselves. There's a shell that goes around a rack. If you don't have to have a bunch of that shell, then you're obviously saving power. And it adds about an additional 10%-ish to the operational carbon efficiency by saving all of that extra equipment again. So it's not just the servers that you are affecting here with this kind of efficiency. It is also the additional equipment that goes into servicing all that server infrastructure to begin with. So by reducing embodied carbon, you are still actually affecting the operational carbon part of the equation. Really kind of pulling it all together, you can actually save quite a bit. Now, we did some fun carbon equivalencies with this. These are based on the EPA calculator that gives you the ability to kind of make fun equivalencies through those metric tons of carbon I talked about in the last slide. So the amount of, in 1 year, in our fictitious but model data center of 100,000 square feet, we can basically translate the amount of carbon that is saved by the Ampere infrastructure over 1 year into 245,000 acres of forest. That equivalency, about that amount from the carbon saved there, to 40,000 cars taken off the road, 44,000 powered homes in the United States, and my favorite is 3.5, almost, million tree seedlings planted in an urban setting and grown over 10 years. So this is a lot of carbon. This is where the path to sustainability starts, is to just consume less. Do more with less. That is where the path to net zero comes. Let's give some more time to the renewable energy people who are doing great work. All of the Google PPAs that are happening by large companies out there, really kind of doing the right thing, sponsoring green technology in the power generation industry. They need more time. They need more time to get that stuff done. And if we can give them more time, then by lowering the amount of electricity consumed in the first place, we are going to get to net zero much quicker. All right, so I'm going to close with a couple of other thoughts. We are a company that is changing the trajectory. The trajectory is get more compute dense. That means that at the performance per data center kind of level, we are creating technology that will allow us to grow. Not just grow our industry in terms of the amount that we can compute, but also grow our ability to create sustainable data centers. It's just different. And that is a key to kind of building these sustainable data centers in the future. Now, our call to action, you saw it from my colleague Madhu earlier. Go and check us out. We've got a lot of information. All of the background that I just walked you through is on our website. It's under our efficiency campaign. So you can actually go and check our math. There's a bunch of information there on actual performance for very, a wide range of applications from, AI to databases to cloud gaming, whatever. There's a ton of application data out there. And you can also get access to useful information about how to implement things on our architecture. Since it's ARM-based, some people have a lot of questions about that. So we have a lot of resources there for that. But assess and evaluate your workloads. Start converting them. Every little bit helps, right? Because this is substantial, and it's one of the things that we need to do to be responsible citizens in the world today. Now, finally, I will be on in just a moment with my friend Peter Groth, and we're going to talk to you a little bit more about one of the manifestations of our processing architecture, the RL300. And then I'd love to have you join Jayesh tomorrow, and he's going to talk a little bit more about Mount Bonnell, which is a half-width sled, getting, again, more compact with our compute. And also join us out in the foyer, in the exhibits, and we'd love to talk to you more about what we're doing and how we're doing it out there. So I appreciate your attention today, and have a great rest of your event.